The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's start. So, in this class we focused mostly on having some slab of material and having some configuration of some kind of a field inside. And we said that basically we are going to be interested close to, let's say, phase transition and some quantity that changes at the phase transition. We are interested in figuring out the singularities associated with that. And we can coarse grain. Once we have coarse grained, we have a field M, potentially a vector, that is characterized throughout this material. So it's a field that's function of x. And by integrating out over a lot of degrees of freedom, we can focus on the probability of finding different configurations of this field. And this probability we constructed on the basis of a number of simple assumptions, such as locality, which implied that we would write this probability as a product of contributions of different parts, which in the exponent becomes an integral. And then we would put within this all kinds of things that are consistent with the symmetries of the problem. So if, for example, this is a field that is invariant under rotations, we would be having terms such as m squared, m to the fourth, and so forth. But the interesting thing was that, of course, there is some interaction between neighborhoods. Those neighborhood interactions we can, in the continuum limit, implement by putting terms that are proportional to gradient of m and so forth. So there's a lot of things that you could put consistent with symmetry, and presumably being as general as possible, you could have this, and the terms in this coefficients of this expansion would be these phenomenological parameters characterizing this probability, function of all kinds of microscopic degrees of freedom, as well as macroscopic constraints such as temperature, pressure, etc. Now the question that we have is, if I start with a system, let's say a configuration where everybody is pointing up, or some other configuration that is not the equilibrium configuration, how does the probability evolve to become something like this? Now, we are interested, therefore, in m, that is a function of position and time. And since I want to use t for time, this coefficient of m squared that we were previously calling t, I will indicate by r. Okay? There are various types of dynamics that you can look at for this problem. I will look at a class that is dissipative. And its inspiration is the Brownian motion that we discussed last time, where we saw that when you put a particle in a fluid, to the good approximation when the fluid is viscous, it is the velocity that is proportional to the force, and you can ignore inertial effects such as mass times acceleration, and you write an equation that is linear in position. Velocity is the linear derivative of position, which is the variable that is of interest to you. So here the variable that is of interest to us is this magnetization that is changing as a function of time. And the equation that we write down is the derivative of this field with respect to time. And again, for the Brownian motion, the velocity was proportional to the force. The constant of proportionality was some kind of a mobility that you would have in the fluid. So continuing with that inspiration, let's put some kind of a mobility here. I should really put a vector field here, but just for convenience, let's just focus on one component and see what happens. Now, what is the force? Presumably, each location individually feels some kind of a force. And typically, when we had the Brownian particle, the force we were getting from the derivative of the potential with respect to variation of the position, the field that we are interested in. So the analog of our potential is this free energy that we have over here. And in the same sense that we want this effective potential, if you like, to govern the equilibrium behavior, and again, recall that for the case of the Brownian particle, eventually the probability was related to the potential by e to the minus beta v. This is the analog of our beta v, now considering the entire field. So the analog of the force is a derivative of this beta h. So this would be our beta h with respect to the variable that I'm trying to change. And since I don't have just one variable but a field, the analog of the derivative becomes this functional derivative. And in the same sense that the Brownian particle, the Brownian motion is trying to pull you towards the minimum of the potential, this is an equation that if I kind of stop over here, tries to put the particle towards the minimum of this beta h. Now, the reason that the Brownian particle didn't go and stick at one position, which was the minimum, but fluctuated, was of course that we added the random force. So there is some kind of an analog of a random force that we can put either in front of mu, or imagine that we added it to mu and we put it over here. Now, for the case of the Brownian particle, the assumption was that if I evaluate eta at some time and eta at another time, t2 and t1, that this was related to 2D delta function t1 minus t2. Now, of course, here at each location, I have a noise term. So this noise carries an index which indicates the position, which is of course a vector in d dimension in principle. And there is no reason to imagine that the noise here that comes from all kinds of microscopic degrees of freedom that we have integrated out should have correlation with the noise at some other point. So the simplest assumption is to also put a delta function in the positions. Okay? So if I take this beta h that I have over there and take the functional derivative, what do I get? I will get that dm of xt by dt is the functional, oops, and I forgot to put a minus sign here. The force is minus the potential, and this is basically going down the gradient, so I need to put that. So I have to take a derivative of this. First of all, I can take a derivative with respect to m itself. I will get minus rm, and then I will get, well, actually, let's put the minus out front. And then I will get the derivative of m to the fourth, which is 4u m cubed, all kinds of terms like this. then the terms that come from the derivatives, and taking the derivative with respect to gradient will give me k times the gradient, but then in the functional derivative, I have to take another derivative, converting this to minus k Laplacian of m, and then I would have L, the fourth derivative from the next term, and so forth. And on top of everything else, I will have the noise whose statistics I have indicated above. Okay? So this entity, this equation, came from the Landau-Ginzburg model, and it is called the time-dependent Landau-Ginzburg equation. And so would be the analog of the Brownian type of equation now for an entire field. Now, we're going to have a lot of difficulty in the short amount of time that is left to us to deal with this nonlinear equation. So we're going to do the same thing that we did in order to capture the properties of the Landau-Ginzburg model qualitatively, which is to ignore the nonlinearity. So it's a kind of Gaussian version of the model. So what we did was we linearized.
Question?
Yes?
Why does the sign in front of the k term change relative to the others?
Okay, so when you have a function null of a field, gradient, etc., you can show that the functional derivative, the first term is the ordinary type of derivative, and then if you think about the variations that occur in M, and with the gradient, and you write it as M plus delta M, and then make sure that you take the delta M outside, you need to do an integration by part that changes the sign, and the next term would be the gradient of d phi by the grad M, and the next term would be Laplacian of d2 phi by the gradient of m squared, and so forth. It alternates, and so by explicitly calculating the difference of two functionals with this integration evaluated at m and m plus delta m, and pulling out everything that is proportional to delta m, you can prove this expression. Okay? So we linearize this equation, which is I've already done that. I cross out the m cubed term and any other nonlinear term, so I only keep the linear term. And then I do a Fourier transform. So basically, I switch from a position representation to the Fourier transform, let's say, call it m tilde of q and t. X is replaced with q. And then the equation for the field M linear form separates out into independent equations for the components that are characterized by q. So the Fourier transform of the left-hand side is just this. Fourier transform of the right-hand side will give me minus mu r plus k q squared. The derivative of Laplacian will give me a minus q squared. And the derivative of the next term, L cubed to the fourth, etc. And I've only kept the linear term. So I have m tilde of q and t. And then I have the Fourier transform of the noise eta of x and t becoming eta tilde of q and t. Okay? So you can see that each mode satisfies a separate linear equation. Right? So this equation is actually very easy to solve. For an linear equation, m tilde of q and t, if I didn't have the noise, so I would start with some value at t equals to 0, and that value would decay exponentially with a characteristic time that I will call tau of q, and 1 over tau of q is simply this mu r plus k q squared and so forth. Now, once you have noise, essentially each one of these noises acts like an initial condition, and so the full answer is an integral over all of these noises from 0 till the time t of interest, dt prime, the noise that occurs at time t prime, and the noise that occurs at time t prime relaxes with this e to the minus t prime tau of q. So that's the solution to that linear noisy equation. Basically, simple thing to check. Okay? So one of the things that we now see is that essentially the different Fourier components of the noise, the different Fourier components of the field, each one of them is independently relaxing to something, and each one of them has a characteristic relaxation time. As I go towards smaller and smaller values of q, this rate becomes smaller and the relaxation time becomes larger. So essentially, short wavelength modes that correspond to large q will relax first. Longer wavelength modes will relax later on. And you can see that the largest relaxation time, tau max, corresponds to q equals to 0, is simply 1 over mu r. Right? So I can plot this tau max as a function of r. And again, in this theory, the Gaussian theory we saw only makes sense as long as r is positive. So I have to look only on the positive axis. And I find that the relaxation time for the entire system, for the longest wavelength, actually diverges as r goes to 0. And recall that r, in our perspective, is really something that is proportional to t minus tc. So basically, we find that as we are approaching the critical point, the time it takes for the entirety of the system, or the longest wavelength modes, to relax diverges as 1 over t minus tc. There's an exponent that shows this so-called critical slowing down. Yes?
In principle, why couldn't you have that r becomes negative if you restrict your range of q to be outside of some value and not go arbitrarily close to the origin?
You could, but what's the physics of that? See?
I'm wondering if there is, or is that not needed?
No. Okay, so the physics of that could be that you have a system that has some finite size, L. Then the largest q that you could have would be of the order, the smallest q that you could have would be of the order of 1 over L. So in principle, for that you can go slightly negative. You still cannot go too negative because ultimately this will overcome that. But again, we are interested in singularities that we kind of know arise in the limit of L being very large. Okay? Now also recall there is a time that we see is diverging as r goes to 0. Of course, we identified before a correlation length from balancing these two terms, and the correlation length is square root of k over r, which is again proportional to t minus tc, and diverges with the square root singularity. So we can see that this tau max is actually related to psi squared over mu k. And it is also related towards this. We can see that our tau of q, basically, if q is large, such that qc is larger than 1, then the characteristic time is going to be 1 over mu k times the inverse of q squared. And the inverse of q is something like a wavelength. Whereas ultimately this saturates for qc that is less than 1 along wavelengths to c squared over mu k. So basically, you will be seeing things at very short range at length scales that are much less than the correlation length of the system, that the characteristic time will depend on the length scale that you are looking at squared. Okay? Now, you have seen times scaling as length squared from diffusion. So essentially, this is some kind of a manifestation of diffusion. That is, you perturb the system, let's say at short distances. There's some equilibrium system, and let's say we do some perturbation to it at some point. Then that perturbation will start to expand diffusively until it reaches the size of the correlation length, at which point it stops. Because essentially, a correlation length is an individual block that doesn't know about the individual block, so the influence does not pass. Okay? So quite generally, what you find, so we solve the linearized version of the Landau-Ginzburg model, but we know that, say, the critical behaviors for the divergence of the correlation length that is predicted here is not correct in 3 dimensions. Things get modified. So this kind of exponents that comes from diffusion also gets modified. And quite generally, you find that the relaxation time of a mode of wavelength q is going to behave something like wave number rather than to, or wavelength, which is 1 over q, rather than squared as some exponent z. And then there is some function of the product of the wavelength you are looking at and the correlation length, so that you will cross over from one behavior to another behavior as you are looking at length scales that are smaller than the correlation length or larger than the correlation length. And to get what this exponent z is, you have to do study of the nonlinear model, in the same sense that in order to get the correction to the exponent mu, we had to do epsilon expansion. You have to do something similar, and you'll find that at higher changes, the way it goes like some correction that does not actually start at order of epsilon, but at order of epsilon squared. But there's essentially some modification of the qualitative behavior that we can ascribe to diffusion of independent modes exists quite generally, and universal exponents different from 2 will emerge from that. Okay? Now, turns out that this is not the end of the story. Because we have seen that the same probability distribution can describe a lot of different systems. Let's say we focus on the case of n equals to 1. So then the Landau-Ginzburg that I described for you can describe, let's say, the Ising model, which describes magnetic fields that lie along the particular direction, magnetizations that lie along the particular direction. We said that it can also describe liquid-gas phenomena, where the order parameter is the difference in density, if you like, between the liquid and the gas. Yet another example that it describes is the mixing of an alloy. So let's, for example, imagine brass that has a composition X that goes between 0 and 1. On one end, let's say you have entirely copper. On the other end, you have entirely zinc. And so this is how you make brass as an alloy. And what my other axis is the temperature. What you find is that there is some kind of a phase diagram such that you get a nice mixture of copper and zinc only if you are at high temperatures. Whereas if you are at low temperature, you basically will separate into chunks that are rich in copper and chunks that are rich in zinc, and you have a critical demixing point which has exactly the same properties as the Ising model. For example, this curve would be characterized with an exponent beta, which would be the beta of the Ising model. Okay? And in particular, if I were to pick someplace in the vicinity of this and try to write down a probability distribution, that probability distribution would be exactly what I have over there, where m is, let's say, the difference between the two types of alloys that I have compared to each other over here. So this is related to 2x minus 1 or something like that. Doesn't matter. Okay? So as you go across your piece of material close to here, there will be compositional variations that are described by that. So the question is, I know exactly what the probability distribution is for this system to be in equilibrium given this choice of m. Again, with some set of parameters r, u, etc. Question is the dynamics again described by the same equation? And the answer is no. The same probability distribution can describe or can be obtained by with very different dynamics. And in particular, what is happening in the system is that if I integrate this quantity m across the system, I will get the total number of one minus the other, which is what is given to you. And it does not change as a function of time. d by dt of this quantity is 0, cannot change. Okay? Whereas the equation that I have written over here, in principle, locally I can, by adding noise or by bringing things from the neighborhood, I can change the value of m. I cannot do that. So this process of the relaxation that would go on in beta brass cannot be described by the time-dependent Landau-Ginzburg equation because you have this conservation. Okay? So what should we do? Well, when things are conserved, like, say, as the gas particles move in this fluid, and if I'm interested in the number of particles in some cube, then the change in the number of particles in some cube in this room is related to the gradient of the current that goes into that place. So the appropriate way of writing an equation that describes, let's say, the magnetization changing as a function of time, given that you have a conservation law, is to write it as minus the gradient of some kind of a current. So this J is some kind of a current. These would be vectors. This is a current of the particles moving into the system. Now, in systems that are dissipative, currents are related to the gradient of some density through the diffusion constant, etc. So it kind of makes sense to imagine that this current is the gradient of something that is trying, or more precisely, minus the gradient of something that tries to bring the system to be more or less in its equilibrium state. The equilibrium state, as we said, is determined by this beta h, and we want to push it in that direction. So we put our d beta h by dm over here. And we put some kind of a mu over here. Of course, I would have to add some kind of a conserved random current also, which is the analog of this non-conserved noise that I add over there. Okay? Now, the conserved version of the equation, you can see will have two more derivatives with respect to what we had before. And so once I, okay, so it will be something like this. dm by dt is mu c, and then I would have Laplacian of r rather than r itself. Actually, it would be Laplacian of something like rm plus 4um cubed, and so forth. But we are going to ignore this kind of term. And then there would be higher order terms that would show up, minus k, the fourth derivative, and so forth. And then there will be some kind of a conserved noise that I have to put outside here. Okay. So when I Fourier transform this equation, what do I get? I will get that dm by dt is, let's say in the Fourier space, m tilde as a function of q and t, is minus mu c. Because of this Laplacian, there's an additional factor of q squared. And then I have r plus kq squared plus lq to the fourth, etc. And then I will have a Fourier transform version of this conserved noise. You can see that the difference between this equation and the previous equation is that all of the relaxation times will have an additional factor of q squared. And so eventually, the shortest relaxation time actually will grow like the size of the system squared, whereas previously it was saturated at the correlation length. And because you have this conservation law, you have to rearrange a lot of particles, keeping their numbers constant. You have a much harder time of relaxing the system, all of the relaxation times, as we see, go correspondingly and become higher. Okay? So indeed, for this class, one can show that Z starts with 4, and then there will be corrections that would modify that. So yes?
How do we define and how do we do a realization of a conserved noise, conserved current, conserved noise current?
Okay.
So it has some kind of like correlation, self-correlation properties, I suppose, because like if current flowing out of some region, the same amount should be flowing in.
If I go back here, I have a good idea of what is happening, because all I need to, in order to ensure conservation, is that dm by dt is the gradient of something.
Okay.
So I can put whatever I want over here.
So it's a scalar noise field.
Yes, as long as it is sitting under the gradient, it will be okay, which means that this quantity here that I'm calling eta c has a gradient in it. And if you wait for about 5 minutes, we'll show that because of that in Fourier space, rather than having, well, I'll describe the difference between non-conserved and conserved noise in Fourier space. It's much easier. Okay? So actually, as far as what I have discussed so far, which is relaxation, I don't really need the noise, because I can forget the noise, and all I have said, and I forgot the m tilde, is that I have a linear equation that relaxes your variable to 0. I can immediately read off what the correlation length is. Correlation time is. What I need the noise for is so that ultimately I don't go to the minimum of the potential, but I go to this probability distribution. So let's see what we have to do in order to achieve that. For simplicity, let's take this equation, although I can take the corresponding one for that. So, and let's calculate, because of the presence of this noise, if I run the same system at different times, I will have different realizations of the noise. Or if I had run many versions of the system because of the realizations of noise, this quantity m tilde would be different. It would satisfy some kind of a probability distribution. So what I want to do is to calculate averages, such as the average of m tilde, let's say q1 at time t with m tilde q2 at time t. And you can see already from this equation that if I forget the part that comes from the noise, whatever initial condition that I have will eventually decay to 0. So the thing that agitates and gives some kind of a randomness to this really comes from this. So let's imagine that we have looked at times that are sufficiently long so that the influence of the initial condition has died down. I don't want to write the other term. I could do it, but it's kind of boring to include it. So let's forget that and focus on the integral, 0 to t. Now, if I multiply two of these quantities, I will have two integrals over t prime. Right? Each one of them would decay with the corresponding tau of q. In one case, tau of q1. In the other case, tau of q2, coming from these things. And the noise, q1 at time t1 prime, the noise q2 at time t2 prime. Okay? Now, if I average over the noise, then I have to do an average over here. Okay? Now, one thing that I forgot to mention right at the beginning is that, of course, the average of this we are going to set to 0. It's the variance that is important, right? So if I do that, clearly the average of one of things in Fourier space would be 0 also, because the Fourier Q is related to the real space eta just by an integral. So if the average of the integral is 0, the average of this is 0. So it turns out that when you look at the average of two of them, and it's a very simple exercise to just rewrite these things in terms of eta of x and t, eta of x and t, and apply the average that you have. And you will find that the things that are uncorrelated in real space also are uncorrelated in Fourier space. And so the variance of this quantity is 2d delta t1 prime minus t2 prime. And then you have the analog of the delta function in Q space, which always carries this additional factor of 2 pi to the d, and it becomes a sum of the Q's, as we've seen many times before. Okay. So because of this delta function, this double integral becomes one integral. So I have the integral 0 to t. The two t primes I can write as just one t prime. And these two factors merge into one, becomes e to the minus t minus t prime over tau of q, except that I get multiplied by a factor of 2, since I have two of them. And outside of the integral, I will have this factor of 2d and then 2 pi to the d delta function q1 plus q2. Okay. Now we are really interested, and I already kind of hinted at that, in the limit where time becomes very large. In the limit where time becomes very large, essentially I need to calculate the limit of this integral as time becomes very large. As time goes to very large, this is just the integral from 0 to infinity, and the integral is going to give me 2 over tau of q. Essentially, you can see that integrating at the upper end will give me just 0. Integrating at the smaller end will be exponentially small as t goes to infinity. There's a factor of 2 over tau. Okay? Yes?
Are you assuming, or are you assuming that tau of q is even in q to be able to combine the
Yes.
two taus? Okay.
I'm thinking of the tau of q's that we've calculated over here. Okay? Yes?
Here, the eta is derivative, the gradient of something, right? So
At this stage, I'm focusing on this expression over here, where eta is not. But I will come to that expression also. So, right. So for the time being, this d is just the same constant as we have over there. Okay? So you can see that the final answer is going to be d over tau of q, 2 pi to the d delta function q1 plus q2. And if I use the value of tau of q that I have, tau of q is mu r plus kq squared. This becomes d over mu r plus kq squared, and so forth. 2 pi to the d delta function q1 plus q2. So essentially, if I take this linearized time-dependent Landau-Ginzburg equation, run it for a very long time, and look at the correlations of the field, I see that the correlations of the field at the limit of long times satisfy this expression. Now, what do I know if I look at the top line that I have for the probability distribution? I can go and express that probability distribution in Fourier modes. In the linear version, I immediately get that the probability of m tilde of q is proportional to a product over different q's, e to the minus r plus k q squared, etc., m tilde of q squared over 2. Right? So when I look at the equilibrium linearized Landau-Ginzburg, I can see that if I calculate the average of m of q1, m of q2, where this is an equilibrium average, what I would get is 2 pi to the d delta function of q1 plus q2, because clearly the different q's are decoupled from each other. And for a particular value of q, what I will get is 1 over r plus k q squared, and so forth. Yes?
Sorry, isn't the 2 over tau, shouldn't it be tau over p when we did the integral?
Yes. Over 2. Yeah. Okay. Okay. Actually, because I had 2d, cancels the 2. But I would have to put here tau of q over 2. I had 2d times tau of q over 2. So it's d tau, and inverse of tau I have written correct. Okay. So if you make an even number of errors, the answer comes out. Okay, but you can now compare this expression that comes from equilibrium and this expression that comes from the long time limit of this noisy equation. Okay? So we want to choose our noise so that the stochastic dynamics gives the same value as equilibrium, just like we did for the case of a Brownian particle, where we had some kind of an Einstein equation that was relating the strength of the noise and the mobility. And we see that here, all I need to do is to ensure that d over mu should be equal to 1. Okay? Now the thing is that if I am doing this, I in principle can have a different noise for each q and compensate by different mobility for each q, and I would get the same answer. So in the non-conserved version of this time-dependent dynamics that we wrote down, the d was a constant and the mu was a constant. Whereas if we want to get the same equilibrium result out of the conserved dynamics, we can see that essentially what we previously had as mu became something that is proportional to q squared. So essentially here this becomes mu c q squared. So clearly, in order to get the same answer, I have to put my noise to be proportional to q squared also. And we can see that this kind of conserved noise that I put over here achieves that. Because as I said, this conserved noise is the gradient of something, which means that when I go to Fourier space, it will be Q, will be proportional to Q. And when I take its variance will be proportional to Q squared, and it will precisely cancel that. But you can see that you also, this had a physical explanation in terms of a conservation law. In principle, you can cook up all kinds of D of Q and mu of Q, and as long as this equality is satisfied, you will have, for these linear stochastic equations, the guarantee that you would always get the same equilibrium result. That is, if you wait for the dynamics to settle down after long times, you would get to the same answer. Yes?
I wonder how general is this result for stochastic dissipative systems?
Okay. So what I showed you was for a linearized version, and the only thing that I calculated was the variance. And I showed that the variances were the same, and if I have a Gaussian probability distribution, the variances completely characterize the probability distribution, so this is safe. But we are really interested in a more general non-Gaussian probability distribution. So the question really is, if I keep the full nonlinearity and this story, would I be able to show that the probability distribution that will be characterized by all kinds of moments eventually has the same behavior as that? And the answer is in fact yes. There's a procedure that relies on converting this equation, to an equation that governs the evolution of the full probability as a function of time. Right? So basically, I can start with an initial probability and see how this probability evolves as a function of time. And this is sometimes called the master equation, sometimes called the Fokker-Planck equation. And we will cover, in fact, this in next spring in the statistical physics in biology. We spend some time talking about these things, so you can come back to the third version of this class. And one can show that with appropriate choice of the noise, the asymptotic solution for this probability distribution is whatever Landau-Ginzburg or other probability distribution that you impose.
So this is true if we assume Landau-Ginzburg potential for our system.
Yes.
Maybe this is not a very good stated question, but is there kind of like even more general level?
I'll come to that shortly. But currently, the way that I set up the problem was that we know some complicated equilibrium force that formed of the probability that exists, and these kinds of stochastic linear or nonlinear evolution equations, generally called Langevin equations, one can show that with the appropriate choice of the noise, we'll be able to asymptotically reproduce the probability distribution that we knew. But now the question is, suppose you don't know the probability distribution, and I'll say a few words about that.
Okay, thank you.
Anything else? Okay? So the lesson of this part is that the field of dynamical critical phenomena is quite rich, much richer than the corresponding equilibrium critical phenomena, because the same equilibrium state can be obtained by various different types of dynamics. And I explained to you just one conservation law, but there could be some combination of conservation of energy, conservation of something. So there is a whole listing of different universality classes that people have tabulated for the dynamics. But now all of this was assuming that you know what the ultimate answer is, because in all cases, the equations that we were writing depended on some kind of a gradient descent conserved or non-conserved around something that corresponded to the log of the probability distribution that you eventually want to go to. And maybe you don't know that. And so let me give you a particular example in the context of, let's say, surface interface fluctuations. Starting from things that we know and then building to something that maybe we don't. Let's first start with the case of a soap bubble. So we take some kind of a circle or whatever, and we put a soap bubble on top of it. And in this case, the energy of deformation, the cost of deformation, comes from surface tension. And let's say the cost of the deformation is the change in area times some sigma so I will neglect the contribution that comes from the flat surface and say if I make a deformation, I have changed the area of this film. So there is a cost that is proportional to the surface tension times the change in area. Change in area locally is the square root of 1 plus the gradient of a height profile. So what I can do is I can define at each point on the surface how much it has changed its height from being perfectly flat. So h equals to 0 is flat. Local area is the integral dx dy of square root of 1 plus gradient of h squared minus 1 that corresponds to the flat. And so when you expand that, the first term is going to be integral gradient of h squared. So this is the analog of what we had over there, only the first term. So you would say that the equation that you would write down for this would be up to some constant mu proportional to the variations of this, which will give me something like sigma Laplacian of h. But because of the particles from the air constantly bombarding the surface, there will be some noise that depends on where you are on the surface in time. And this is the non-conserved version. And you can from this very quickly get that the expectation value of h tilde of q squared is going to be proportional to something like d over mu sigma q squared because of this q squared. And if you ask how much fluctuations you have in real space, so the typical scale of the fluctuations in real space will come from integrating 1 over q squared, and it's going to be our usual things that have this logarithmic dependence. So there will be something that ultimately will grow logarithmically with the size of the system. The constant of the proportionality will be proportional to kt over sigma. So you have to choose your d and mu to correspond to this. But basically, a soap film, as an example of all kinds of Goldstone mode-like things that we have seen, it's a two-dimensional entity, will have logarithmic fluctuations. Not very big, but ultimately, at large enough distances, it will have fluctuations. So that was non-conserved. I can imagine that rather than this, I have the case of a surface of a pool. So here I have some depth of water, and then there's the surface of the pool of water. And the difference between this case and the previous case, both of them can be described by a height function. The difference is that if I ignore evaporation and condensation, the total mass of water is going to be conserved. So I would need to have d by dt of the integral d2x h of x and t to be 0. Okay? So this would go into the conserved variety. And while if I create a ripple on the surface of this compared to the surface of that, the relaxation time through this dissipative dynamics would be much longer in this case as opposed to that case. Ultimately, if I wait sufficiently long time, both of them would have exactly the same fluctuations. That is, you would go logarithmically with the length scale over which we are looking at. Okay, so now let's look at another system that fluctuates, and I don't know what the final answer is. So that was the question maybe that you asked. The example that I will give is the following. So suppose that you have a surface, and then you have a rain of sticky materials that falls down on top of it. Okay? So this material will come down. You have something like this. And then as time goes on, there will be more material that will come, more material that will come, more material that will come. So because the particles are raining down randomly at different points, there will be a stochastic process that is going on. So you can still try to characterize the system in terms of a height that changes as a function of t and as a function of position. And there could be all kinds of microscopic things going on, like maybe these are particles that are representing some kind of a deposition process, and when they come, they stick in a particular way. Maybe they can slide on the surface. You can imagine all kinds of microscopic degrees of freedom and things that you can put. But you say, well, can I change my perspective and try to describe the system the same way that we did for the case of coarse graining and going from without the microscopic details to describe the phenomenological Landau-Ginzburg equation? And so you say, okay, there is a height that is growing, and what I will write down is an equation that is very similar to the equations that I had written before. Now, I'm going to follow the same kind of reasoning that we did in the construction of this Landau-Ginzburg model. Is we said that, well, this weight is going to depend on all kinds of things that relate to this height that I don't quite know. So let's imagine that there is some kind of a function of the height itself, and potentially just like we did over there, the gradient of the height, higher derivatives of the height, etc. Okay? And then I will start to make an expansion of this in the same spirit that I did for the Landau-Ginzburg model. Except that when I was doing the Landau-Ginzburg model, I was doing the expansion at the level of looking at the probability distribution and the log of the probability. Here I'm making the expansion at the level of the equation that governs the dynamics. Okay? Of course, in this particular system, that's not the end of the story, because the change in height is also governed by this random addition of the particles. So there is some function that changes as a function of position and time, depending on whether at that time a particle was dropped down. I can always take the average of this to be 0 and put that average into the expansion of this starting from a constant. Basically, if I just have a single point and I randomly drop particles at that single point, there will be an average growth velocity, an average addition to the height. That average is over here, but there will be fluctuations that are going around it. Okay? But the constant is the first term is in an expansion such as this, and you can start thinking, okay, what next order? Can I put something like alpha h? potentially depends on your system. But if the system is invariant, whether you started from here or whether you started from there, if something like gravity, for example, is not important, you say, okay, I cannot have any function of h if my dynamics would proceed exactly the same way if I were to translate this surface to some further up or further down. If I see that there is no change in future dynamics on average, then the dynamic cannot depend on this. Okay, so we got rid of that. And any function of h, can I put something that is proportional to gradient of h? Maybe for something I can, but for h itself I cannot, because h is a scalar, gradient of h is a vector. I can't set something that is a scalar equal to a vector, so I can't have this. Right? Yes?
Could you, in principle, make your constant term in front of the gradient also a vector and take the dot product?
You could. So there is a whole set of different systems that you can be thinking about. Right now, I want to focus on the simplest system, which is a scalar field, so that my equation will be as simple as possible, but still, we will see has sufficient complication. Okay? So you can see that if I don't have, then the next order term that I can have would be something like a Laplacian. Okay? So a kind of diffusion equation, you can see, has to emerge as a low order expansion of something like this. I mean, this is the ubiquity of the diffusion equation appearing all over the place. And then you could have terms that would be of the order of a fourth derivative and so forth. There is nothing wrong with that. And then, if you think about it, you'll see that there is one interesting possibility that is not allowed for that system, but is allowed for this system, which is something that is a scalar. It's the gradient of h squared. Now, I could not have added this term for the case of the soap bubble for the following reason. That if I reverse the soap bubble so that h becomes minus h, the dynamics would proceed exactly as before. So the soap bubble has a symmetry of h going to minus h. And so that symmetry should be preserved in the equation. This term breaks that symmetry because the left-hand side is odd in h, whereas the right-hand side with this term would be even in h. But for the case of the growing surface, and you've seen things that are growing, and typically if I give you something that has grown, like the tree trunk, for example, and if I take the picture of a part of it, and you don't see where the center is, where the end is, you can immediately tell from the way that the shape of this object is that it is growing in some particular direction. So for growth systems, that symmetry does not exist. You are allowed to have this term and so forth. Now, the interesting thing about this term is that there is no beta h that you can write down that is local, some function of h, such that if you take a functional derivative with respect to h, it would reproduce that term. Just does not exist. So we can see that somehow immediately, as soon as we liberate ourselves from writing equations that came from functional derivative of something, but potentially have physical significance, we can write down new terms. So this is actually also, you can do this even for two particles. A potential v of x1 and x2 will have some kind of derivatives. But if you write dynamical equations, there are dynamical equations that allow you to rotate x from x1 to x2. That kind of term will never come from taking the derivative. Okay? So, fine. So this is a candidate equation that is obtained in this context. Something that is grown, we say we are not interested in it's coming from some underlying weight, but presumably this system still, if I look at it at long times, will have some kind of fluctuations. Are the fluctuations of this growing surface like the fluctuations of the soap bubble, and they have this logarithmic dependence? That's the question.
So why doesn't that term, like, what if I put in an h times that term that we want to appear, and then I vary with respect to h? A term like what we want will pop out together with other terms, right?
Yeah, but those other terms, what do you want to do with them?
Well, they're not acceptable in the 6 one.
No. So you're saying, why not have a term that is h gradient of h squared? Functional derivative of that is gradient of h squared, and then you have a term that is h Laplacian, it's a gradient of h, gradient of h, okay? And when you expand this, among the terms that you would generate would be a term that is h Laplacian of h. This term violates this condition that we had over here, right? And you cannot separate this term from that term. So what you described, you already see at the level over here. It violates translational symmetry. And you can play around with other functions, you'll come to the same conclusion. Okay, so the question is, fine, you added some term here. If I look at this surface that is grown at large time, does it have the same fluctuations as we had before? Okay, so a simple way to ascertain that is to do the same kind of dimensional analysis, which for the Landau-Ginzburg was a prelude to doing renormalization. So we did things like epsilon expansion, etc. But to calculate that there was a critical dimension of 4, all we needed to do was to rescale x and m, and we would immediately see that u goes to u b to the 4 minus d or something, d minus 4, for example. So we can do the same thing here. We can always move to a frame that is moving with the average velocity so that we are focusing on the fluctuations. So we can basically ignore this term. I'm going to rescale x by a factor of b. I'm going to rescale time by a factor of b to something to the z. And this z is kind of indicative of what we've seen before, that somehow in these dynamical phenomena, the scaling of time and space are related to through some exponent. But there is also an exponent that characterizes how the fluctuations in h grow if I look at systems that are larger and larger. In particular, if I had solved that equation, rather than for a soap bubble in 2 dimensions, for a line, for a string that I was pulling so that I had line tension, the 1-dimensional version of it, the 1-dimensional version of it, integral of 1 over q squared, would be something that would grow with the size of the system. So there I would have a chi of 1/2, for example, in 1 dimension. So this is the general thing. And then I would say that the first equation, dh by dt, gets a factor of b to the chi minus z, because h scaled by a factor of chi, t scaled by a factor of z. The term sigma Laplacian of h gets a factor of b to the chi minus 2 from the 2 derivatives here. Sorry, the z and the 2 look kind of the same. This is a z, this is a 2. And then the term that is proportional to this nonlinearity that I wrote down, actually it is very easy, maybe worthwhile, to show that sigma to the 4th goes with a factor of b to the chi minus 4. It is always down by a factor of two scalings in B with respect to Laplacian. The same reason that when we were doing the Landau-Ginzburg, we could terminate the series at order of gradient squared because higher order derivatives were irrelevant. They were scaling to 0. But this term goes like b to the 2 chi, because it's h squared, minus 2, because there are two gradients. Now, thinking about the scaling of eta takes a little bit of thought, because what we have, we said that the average of eta is 0. The average of eta at two different locations and two different times, it is these particles that are raining down. They are uncorrelated at different times. They're uncorrelated at different positions. There's some kind of variance here, but that's not important to us. If I rescale t by a factor of b, delta of bt, sorry, if I scale t by a factor of b to the z, delta of b to the zx will get a factor of b to the minus z. This will get a factor of b to the minus d. But the noise eta is half of that. So what I will have is b to the minus z plus b over 2 times eta under the rescalings that I have indicated. I get rid of this term, set this divide by b to the chi minus z. So then this becomes dh by dt is sigma b to the z minus 2. Maybe I will write it in red. B to the z minus 2. This becomes sigma to the 4 b to the z minus 4. And then lambda over 2, this is Laplacian of h. This fourth derivative of h, this is Laplacian of h. This term becomes b to the chi plus z minus 2, gradient of h squared. And the final term becomes b to the chi minus d minus z over 2. Okay. B to the minus chi, you're right. And then actually this I forgot. No? Minus chi minus d over 2 minus d over 2. I forgot. C over 2 minus d over 2. Oh, that's fine. Okay. So I can make this equation to be invariant So I want to find out what happens to this system if I find some kind of an equation or some kind of a behavior that is scale invariant. You can see that immediately my choice for the first term has to be z equals to 2. Okay? So basically it says that as long as you are governed by something that is diffusive, so that when you go to Fourier space you have q squared, your relaxation times are going to have this diffusive character where time is distance squared. Actually, you can see that immediately from the equation that is diffusion, time goes like distance squared. So this is just a statement of that. Now, it is the noise that causes the fluctuations. And if I haven't made some simple error, you will find that the coefficient of the noise term becomes scale invariant, provided that I choose it to be z minus d over 2 for chi. And since my z was 2, I'm forced to have chi to be 2 minus d over 2. And let's see if it makes sense to us. So if I have a surface, such as the case of the soap bubble, in 2 dimensions, chi is 0. And 0 is actually this limiting case that could also be a logarithm. If I go to the case of d equals to 1, like pulling a line and having the line fluctuate, then I have 2 minus 1 over 2, which is 1/2, which means that because of thermal fluctuations, this line will look like a random walk. You go a distance x, the fluctuations in height would go like the square root of it. Okay? So all of that is fine. You would have done exactly the same answer if you had just gotten a kind of a scaling such as this for the case of the Gaussian model without the nonlinearities. But for the Gaussian model with nonlinearities, we could also then estimate whether the nonlinearity u is relevant. So here we see that the coefficient of our nonlinearity, this lambda, is governed by something that is chi plus z minus 2. And our chi is 2 minus d over 2. Z minus 2 is 0. So whether or not this nonlinearity is relevant, we can see depends on whether you are above or below 2 dimensions. So when you are below 2 dimensions, this nonlinearity is relevant, and you will certainly have different types of scaling phenomena than what you predict by the case of the diffusion equation plus noise. Of course, the interesting case is when you are at the marginal dimension of 2. Okay? Now, it turns out that when you do proper renormalization group with this nonlinearity, you will find that unlike the nonlinearity of the Landau-Ginzburg, which is marginally irrelevant in 4 dimensions, du by dl was minus u squared. This lambda is marginally relevant. D lambda by dl is proportional to plus lambda squared. It is relevant marginality. It's marginally relevant. And actually, the epsilon expansion gives you no information about what is happening in the system. So people have then done numerical simulations, and they find that there is a roughness that is characterized by an exponent that is something like 0.4. So that when you look at some surface that is grown, it is much, much rougher than the surface of a soap bubble or what's happening on the surface of the pond. And the key to all of this is that we wrote down equations on the basis of this generalization on symmetry that we had learned, now applied to this dynamical system, did an expansion, found one first term, and we found it to be relevant. And it is actually not that often that you find something that is relevant, because then it's a reason to celebrate, because most of the time things are irrelevant and you end up with boring diffusion equations. So find something that is relevant, and that's my last message to you.